Sorry, we're going to get started whether you're sitting down or not. Dave, good. Dave, I haven't seen you in 1,000 years. Wow. Okay.
Do I look the same?
No, you look just exactly as you did. Okay.
Okay, just before we get started with this panel, I want to respond to several questions I've gotten about the presentations. We're uploading them to me at the end of yesterday and the end of today. So I will post a download link tomorrow to all of the representatives of all of the groups. And then sometime over the next few days, the state board staff will put them up on the website. But you'll get the link tomorrow morning to download all of the presentations. So those of you who've been scribbling madly trying to copy everything down, you don't need to do that anymore. So, okay, so we now have the next panel, which is the water contractors. And so
Ms. Dodek and the members of the board, my name is David Fullerton. I'm a Principal Resource Specialist with the Metropolitan Water District. I've been working in water since about 1985, so I'm starting to become an old-timer. That's 27 years. I've been with Met for 10 years, and about the last 7 years I've been pretty much exclusively devoted to trying to understand the ecosystem and how it all fits together. I'll be shepherding this larger group of panelists through our presentation today. We have Paul Hutton. I'll give more introduction later, but we have Paul Hutton, Sheila Green, Chuck Hansen, and Pat Glibbert. And I'll be giving a little intro here at the beginning and then handing off to them after that. We're going to be mostly presenting the written material that we've submitted to you already. We will be presenting some material to supplement things that other parties have identified. I should say, however, that a lot of our material we're reserving for the pelagic workshop in a couple of weeks. That's where we'll start to talk more intensively about fish and relationships to fish. What we'll talk about today mostly is, farther down in the chain. So let me see if I can change the slides. Oh, good. Okay. When I started in water in the 1980s, the conceptual model was something like this. We didn't have X2 and it didn't have low salinity zone in there, but basically it had a line going from flow through the question mark then to more fish. And kind of the exercise back in those days for striped bass or for neomysis shrimp, for example, was to try to find correlations between your target species and flow, and then to try to put those flows into regulations in an effort to promote those species. It didn't work very well, and you don't really hear about those correlations anymore, but that was the conceptual model. And I think to some extent that model is carried over into the present. And if you look at some of a lot of the presentations you've seen, you can really kind of see this model emerging out of that. We have more bells and whistles on the chain now. We have X2 and low salinity zone, and I think there's a lot more recognition of other factors than just flow. But still, this kind of linear chain, I think, is still a pretty powerful mental paradigm for a lot of people. I think it has some problems that we need to recognize, however. It's very linear, kind of assumes that, causation just, moves down the chain. It's very simple. It doesn't really reflect kind of the complexity of the system. And I think it's a little tendentious in the sense that you're kind of assuming that flow is a master variable and then trying to prove it. But the most important point I want to make, and this is a key theme for us, is that mechanism is where the real game is. That is where the scientific effort needs to go, and that's what I think managers and regulators need to really be trying to hone in on. we need to know not just what things are correlated to each other, we need to know why things are correlated to each other, and try to follow the chain across, from flow or turbidity or food or whatever to whatever we're shooting for, which in many cases is more fish. We have to know why that happened. A good example, I think, is the Sacramento split tail, which has a very nice X2 correlation. It's probably the second best correlation behind longfin. And so you look at Sacramento split tail abundance numbers, and your immediate reaction is, well, let's put some more flow in there. That'll push the X2 downstream. We'll get more split tail. Everything will be good. But as we've learned more about split tail, we've learned that the actual mechanism is floodplain inundation upstream, and that really the key action is to probably be modifying weirs, for example, to allow more frequent inundation of the floodplains. Just pushing more water out of the system wouldn't actually give you any benefit, even though there's a correlation. And I think you might argue the same thing for longfin, that the X2 correlation could reflect. You might get more longfin if you release water from reservoirs, but it could also be that there's something about really wet years, a lot of rainfall, a lot of junk coming into the streams off of fields, a lot of sediment blowing into the rivers, local streams in Sassoon Marsh and the Napa River gushing out. There could be something about wet years that's really good for longfin and other fish that can't be really reproduced by opening the spigot in a reservoir. So we just need to be very careful about causation and focus on that rather than on just correlation. And so here's a quote, but you've probably all seen that quote. I tried to find something that would show the complexity a little bit more. This is just scratching the surface. What you have here. This is a very generalized view of the food web, and even that it's overly simplified. You have the sunlight, you've got nutrients, you've got nutrient balances that might be affecting which species of phytoplankton are doing well. You've got clams that maybe were introduced and start eating the phytoplankton. You've got zooplankton that are eating the phytoplankton. You've got clams that are eating the zooplankton. You've got fish that are eating the zooplankton. And then you've got fish that are eating the other fish, and so on. And then and the whole cycle. And when they die, then they all decay, and the whole thing starts over again. And this is just the food web portion of it. To really be more thorough, you would have to have a diagram that included the turbidity of the water, the temperature of the water, salinity of the water, contaminants, what the substratum of the water column looked like, the bathymetry of the system, and so on. I mean, it's a very complex web, and it makes the problem almost look unmanageable, but I think it actually simplifies it because it forces us to think about what are our hypotheses about how cause and effect move through the system. And we can start to parse out those lines and see which ones actually are important and maybe which ones don't seem to make much difference. Okay. I want to talk just a little bit about kind of the historical changes that we've seen in the system. And I say this for two reasons. One is to just, I think, show you as graphically as possible the immense level of change that has been experienced in the ecosystem, both in the Bay Delta system, the Delta, and upstream in the watershed. I mean, this is one of the most transformed landscapes in the world. And part of the reason I do that is just to, I'm hoping to impress upon you the difficulty in moving back towards something that's natural rather than moving forward towards something based on our understanding of the relationships. Okay. This is a conceptualization of what the system probably looked like kind of pre-development, which is to say the whole thing was a wetland out on the Delta. You've got all kinds of dendritic networks out there. A lot of times the water would be in the channels, but at high tides, much of what is in the Delta would be underwater. During storms, much of the delta would be underwater. The point being that the water-land interface was quite variable. There, the whole thing was kind of a gray area. Sometimes, is it land? Is it water? Which one is it? But what we have now is something quite different. We have a very simplified network of channels without all the dendritic aspects to it, and we don't really have a water-land interface anymore. We either have water or we have land. We don't have land that's providing both functions over the course of the year. And so this is just an enormous change in the system. Okay. I think what I'll do is talk about this poster before I go on. I thought it was in the slideshow, but I don't think it is. This poster shows some of the changes as well. A lot of this, I think, comes from something that Contra Costa Water District had submitted at an earlier point. But it makes a lot of the same points here. That tidal marsh acreage has dropped dramatically over time. That's what I was showing you in the delta map. Reservoir capacity has grown, which leads to changes in flow patterns, particularly upstream. And it blocks salmon runs, of course. Irrigated acreage has increased over the years. What we call irrigated acreage used to be called, 100 years ago, you would call it habitat, but it's irrigated acreage now. Diversions and consumptive use have risen, although you can see that there's still pretty healthy a diversity of flow patterns remaining for outflow. The next one down is sedimentation rates, which is something that hasn't gotten a lot of discussion, but it's a real interest of mine. I'm seeing in the data that the delta seems to be getting deeper and deeper over time, and other people have observed this as well, and it looks like the sedimentation rates coming into the delta have dropped significantly over the past few decades, and it's causing lower turbidity in the system, and it's causing the tides to eat away at the bottom of the bay system, and so that could be causing changes as well. And then finally, another one that is frequently not discussed are dramatic changes in the configuration of the channels for flood control and for navigation. In particular, the Sacramento ship channel, which is just a massive widening of the system, which changed the hydrodynamics pretty dramatically. So let me go back to the PowerPoint now. What I show up here are some changes that basically have taken place in just the last 30 years, and even the last 30 years shows very dramatic shifts. The nutrient levels, particularly of nitrogen and ammonium, have gone up quite a bit in the system, whereas phosphate hasn't gone up as much, if at all, because we regulate phosphate. We don't put it in soap anymore, so that's kept that down. As everyone has mentioned, we've had a big explosion in clams, the Potamacorbula, particularly in Sassoon Bay. Diatoms and chlorophyll have crashed, particularly diatoms and total phytoplankton, probably associated with the clams, but also partly associated, we think, with nutrient changes. Turbidity is dropping, particularly in the South Delta. Eurythemra has dropped. That used to be kind of the premier food for the pelagics, a lot of the pelagics that we're concerned about here. It's pretty rare now. Limnoithona, which is a very small zooplankton, now, at least in terms of numbers, dominates the system. Toxic algae up, submerged plants up, which changes, basically the ability of different fish to do well. Predators have gone up dramatically in the system, and pelagics have gone down. So these are just some trends. I want to show you a couple of graphs very quickly. You're probably familiar with a lot of these already. The blue line here is diatoms, and you can see that it looks like it was already dropping as we get into the 70s and 80s. But once the Potamacorbula came in, it took a real dive. And you note that Potamacorbula continues, at least in terms of its density, continues to rise. This is an interesting one because this shows Eurythemra dropping, and then after a time delay, Limnoithona coming up. in terms of mass, this is probably about the right scales. But if you look at the two different y-axes, you see that the limnoithona are at huge densities. It's just that they're very small. I liken it to eating a limnoithona is like going to McDonald's and getting a single chicken McNugget, and it's just not, it's hardly worth doing. Everyone has seen this graph. I think pretty much everyone shows this. This is basically an analysis of estuaries, around the world, and it makes the basic point that food and fish are pretty closely related to each other. So this at least leads us to suspect that to the extent that we have low food and low fish, that may be related in this system. And as food supplies become poorer, that could well be part of why the abundance of some of the pelagic fish seems to be dropping. This is an interesting one. Again, everyone has seen these smelt fall midwater trawl values many times before. The centrarchid predator index is something that I cooked up myself. It's basically the average catch per unit effort of all the different centrarchids in the beach seine. And you can see that it was very low in the 70s and 80s, kind of went up in the 90s, and then it skyrocketed during the 2000s. So that's very interesting. One thing it suggests is that not all fish are doing badly. Fish that people like to catch, as in a sport fishery, are doing actually quite well. It's the pelagics in particular that are doing poorly. And then Ted Summer showed this pie chart last time, which is basically saying that in the beach seine in 1981, we had, even then the natives were minority, but there was no single dominant kind of class of fish. But as we move into the more recent years, in the beach seine, which is along the shore, the centrarchids, the bass and sunfish, are really completely dominant, and the natives are very difficult to even find at all. So to summarize our paper, this is the 5 dimensions that we looked at, and basically our paper is a review of the scientific literature in these different dimensions. I should say that the food web carries a lot of baggage. It's not just food, it's also the nutrient effects on food, it's the effect of invasives on food, and so on. And I'll try to summarize these very quickly, and then we'll move on to our other speakers. Basically, the conclusions we came to in reviewing the scientific literature were that the key factors in the food web were probably invasives, nutrients, and what we're calling the water-land interface, which is kind of habitat that's connected to the water system, and includes floodplains. And over those 3, probably nutrients and habitat, or physical landscape changes, are the easiest to do if we want to try to push food back uphill. We've already talked a lot about physical landscape. It's profoundly changed. The changes in the last 20 or 30 years haven't been so profound, but over a longer time scale, the landscape has changed dramatically. Temperature, we've seen increases in temperature in the last several decades, and those are expected to keep going up. And there's a good chance that those temperature changes will have very significant impacts on the ecosystem. Similarly, the turbidity is dropping. It's unlikely we can do much about it. It seems to be related to reduced sediment loading coming in from upstream. And then finally, flows and diversions. Our focus in this paper on flows and diversions was primarily looking at the issue of unimpaired versus natural flows, and then also whether a restoration of natural flows is likely to be highly leveraged. The relationship between flows and the various pelagic species is something that we'll talk a lot more about in the next workshop. Okay, so let me introduce our other speakers, and then I'll give it over to them. I've spoken enough now. Our first speaker will be Paul Hutton, who will be talking about historical flows and historical flow patterns over time. Paul's a senior engineer at Metropolitan. He came on board about the same time I did, about 10 years ago. He was previously head of the DWR Bay Delta modeling section and is an expert in modeling, hydrology, hydrodynamics, and operations. The next speaker after that will be Sheila Green, who is a biologist at the Westlands Water District. And she was formerly a biologist at DWR for 28 years, specializing in ESA issues and the biological impacts of the projects on, well, the impacts of the projects on the biota. The next speaker after that will be Chuck Hansen. I'm sure pretty much everybody knows Chuck Hansen. He's actually the oldest timer that we have here. He doesn't look it, but he's been around the longest. He's been working on these issues for over 30 years and was a member of the U.S. Fish and Wildlife Service Native Delta Fish Recovery Team and the NIMS Central Valley Salmonid Technical Recovery Team. And then finally, our final speaker will be Dr. Pat Glibbert, who is a professor at the University of Maryland with 30 years, actually more than 30 years, so maybe she rivals Chuck here. Sorry, Pat. I shouldn't have said that. I'm sorry. But she has 30-plus years of experience in studying nutrients, food webs, eutrophication, and harmful algae. And she's done these studies throughout the world, which I think is a very useful perspective for us because this system isn't necessarily unique. And in fact, the evidence is that it's not unique at all. So Dr. Glibbert, I think, brings the perspective that she has gained from studying kind of the food web trajectory in other systems where they've had similar shifts in the nutrient balances. Okay, with that, let's move to Paul Hutton.
Good morning, Vice Chair and board members. Oops. Let's see, I just hit the
I use the left button.
left button. My presentation can be summarized in the following 3 points. The first is that unimpaired flow is not the same as natural flow. The second is that climate must be accounted for when we evaluate time trends in flow and salinity. And then the third point is that project operation is not the primary driver of change between the two most recent decades. So the first point, unimpaired is not the same as natural. Unimpaired flow is a calculation. It's not a flow that was ever seen in nature. And you know, you can talk to any of the experts, and this is not at all a controversial point. However, it's often cited that unimpaired flow is a good approximation of what natural conditions are, and that just is not the case. And I'll go into a couple of reasons why. The unimpaired flow calculation assumes that the levees are in place, but under natural conditions, the natural levees were much lower. And when the first flush, high flows came down the system from the mountains, much of that flow would overtop the banks. They would flood the valleys, and much of this water would end up being evapotranspirated by the natural vegetation. And some of it would go to recharging the groundwater, and then the remainder would eventually, throughout the rest of the year, would find its way back to the river and return as delta outflow. So as a result, you can think of it in two ways. One is that in terms of annual volume, the delta outflow, the natural delta outflow was lower and probably quite a bit lower than unimpaired flow is. And then secondly, the unimpaired flow calculation doesn't represent the timing throughout the year because of this regulating effect of the valley. And ironically, the reservoirs actually replace some of that function that the that the levees ended up taking out of the natural system. The second point, channelization and dredging. There's been some discussion about this. Effectively, what that ended up doing was changing the flow-salinity relationship that we see in the delta from natural conditions. Under natural conditions, for the same to maintain the same salinity level, say in Suisun Bay, the outflow would have been much lower in the bay. Then a third point, early 20th century conditions, late 19th century conditions, these also are not representative of what the natural conditions are. And a couple of things, I guess we could partially refer to this graph that's up here, but during that period, much of the marshes had already been drained, levees had been put up, so that natural evapotranspiration was not taking place up in the upstream watersheds. And yet, irrigated agriculture was still in its infancy during that period. So overall, you know, the outflow during that period was artificially high because, compared to natural conditions, because this evapotranspiration wasn't taking place upstream. So now I'm going to move to this point that climate needs to be accounted for when we look at long-term trends. And in this graphic, I'm going to use the 8 River Index as a proxy for climate variability. And this point about climate, this is something that Enright and Culberson in their 2010 paper, they acknowledge that climate is very important. In fact, they state that it is the most important driver in variability in the flow and salinity. So then, you know, just real quickly, this upper graph, what I'm showing is the variability in the 8 River Index, and by, I should explain, the 8 River Index is a measure of the runoff. So this is the annual runoff coming into the valley. And these blue bars are the annual volumes. The black line is a 5-year average. And then the bottom chart is the same data but shown as decadal averages. And I just want to talk about a few features of this time series. And the first is, notice this most recent decade. This most recent decade was very dry when you compare it to our period of record. If you compare it to the 20s and 30s, which you know was a very dry period, as a decadal average, it's right on par with those periods. A second point I want to talk about, again, going back to the early 20th century, late 19th century, certainly there was some discussion about how fresh the bay was during that period, and certainly that was the case. Do note, though, that this period was far and above the wettest period on record. The third point I want to make is there was an assertion in one of the submittals that delta outflow has decreased 40% since the 1950s due to increased water use. I just want to point out in this graph that that type of assertion did not account for climate variability. And you can see here that there's about a 5 million acre-feet difference in runoff between those 2 decades. Now I'm going to show similar graphs, but now we're looking at delta outflow instead of the 8 River Index. And there's a common, looking at the top graph, there's a common misconception that there's been a long-term downward trend in delta outflow. In fact, when you look at the period of record and do a statistical analysis, there is no statistically significant trend in this annual outflow delta or data, either upward or downward. This data is shown as decadal averages in the bottom chart. And just to make point out a few things about the time series. Again, going back to this assertion of decreased delta outflow since the 1950s, That comparison was comparing the highest outflow decade on record and the lowest outflow decade on record, and did not account for all the intervening decades within the period of record. Now, certainly this graphic begs the question, what's happened in this last decade? Why is the delta outflow so low? And I will I'll address that in the next slide. That outflow difference between the 90s and the most recent decade was about 9 million acre feet, about a 9 million acre feet drop. But if we go back to this concept of considering climate variability, most of that can be accounted for just by the dryness. Actually, the unimpaired outflow decreased about 8 million acre feet between the 90s and the current decade. Now, of that remaining amount, about half of that is associated with the project operations. But certainly, you can see that by and large, the climate hydrology is the big driver here. Now I'm going to turn our attention to...
I'm sorry, could you go back to the previous slide?
If I can find the right button,
Okay, that's great. Well, no,
Okay.
right there. So could you provide a little bit more information about that? I accidentally turned on Siri. Your second bar there with respect to the decrease of 8 million acre feet in unimpaired outflow, could you just, if you can briefly, describe how that was calculated?
Yes. That was a difference between the unimpaired outflow volume of the 90s. So if you take that number, the outflow value of the 90s, the calculated unimpaired outflow value of the 90s, and subtract what the, or actually it's the, it would be the difference between the unimpaired outflow of the most recent decade and the outflow difference of the 1990s unimpaired outflow. So the unimpaired outflow in the most recent decade was about 8 million acre feet less than the previous decade. Yes, that is the calculated unimpaired outflow, yes. Okay, now turning our attention to the fall X2 position. I'm going to show you time trends for the months of September and October. And the time trends you're seeing here look quite a bit different than the time trends that others have shown you in their submittals and up here. The main reasons are, number one, I'm looking at the entire period of record as opposed to selecting a period of record, so we don't bias our conclusions by looking at climate periods where we might be comparing one wet period versus a dry period. And secondly, I'm breaking out the individual months of September and October rather than lumping, say, September, October, November, December together. And when you look at the data this way, what you see is that there is a, in fact, instead of the month of September getting saltier, it in effect has been getting fresher over the period of record. And this is a statistically significant decrease, going at about 0.7 kilometers per decade. And the month of October, there is no statistically significant trend in that month. Now I do want to acknowledge that that if you look at the most recent decade, it has certainly been it has been higher in the most recent decade, as many have pointed out to you. What I would like to point, when I point to this record, I'd like to point out that it looks very similar, however, to what we saw before the installation of Shasta Reservoir, which was in the mid-40s. And I will also acknowledge that there were many dry years during this period, but there were many years that were not dry as well. Why I point out this issue about Shasta Dam was When Shasta Dam was put in place, what would have normally been fairly low fall outflows were increased because the reservoirs were capturing winter and spring runoff. There was very little demand in the system at that time, so these reservoirs needed to be drained in the fall for pre-flood control releases. So we see that effect in the 50s, 60s, early 70s, and this was around the time when demands for water were increasing. So that is to say that these weren't, what we're seeing here are not, by no means natural conditions. I'm going to go back here. I wanted to make one other point. About these higher salinities that we've seen in the most recent decade, there has been the assertion that this is due to project operation. And what I'm going to show you in my remaining slides is I want to address that point by showing you graphs like I showed you before. And here I'm going to look at the month of September, and the outflow difference between the 90s and the most recent decade. Outflow did go down about 170,000 acre feet in the most recent decade. But again, if we account for climate, over half of that is due to climate variability. Unimpaired outflow also went down about 100,000 acre feet. And of that remaining amount, very little of this is due to CVP SWP project operation. Now let's look at that same type of graph for October. The most recent decade was drier with delta outflow. It was about 55,000 acre feet less. Now this month is different because we can't attribute to this change to climate variability. In fact, unimpaired outflow increased in the decade by about 14,000 acre feet. However, we can't attribute this decrease in delta outflow to project operations either. In fact, project operations supplemented delta outflow by about 60,000 acre feet. So with that ends my presentation. I just want to go back and just summarize my main points. Number one is that unimpaired flow is not the same as natural flow. Secondly, that we need to account for climate when we're looking at long-term time trends. And then third, the projects are not the primary driver of the outflow differences we saw in the recent decade. Thank you.
Thanks, Paul. Our next speaker will be Sheila Green, talking about the functions that flow provides.
Good morning. I've been working in the Bay Delta for about 25 years now, and I've spent a lot of that time reviewing the literature on the low salinity zone. And I've been involved in the history of regulation of freshwater inflow into this estuary. Even though this estuary has been well studied compared to most, oh, I'm sorry, I forgot about that part. There's still a lot of unresolved uncertainty regarding what flows are necessary to sustain a healthy ecosystem. Much of our current understanding is still based on untested hypotheses, but our situation isn't unique, as you can see by this quote from some noted aquatic ecologists and commented on by Dr. Dahm yesterday. Today, I'm going to go briefly through some areas of uncertainty that I've seen in the literature and how they've been addressed in some of the other submittals. I'd like to make 4 points regarding the natural flow paradigm. First, it was developed for riverine systems, primarily as a conservation measure to protect systems that were largely unaltered. To a lesser extent, it's been used as a restoration tool in more altered systems. But according to POF, the level of uncertainty of success diminishes with the magnitude of alteration that has already occurred. Third, when it has been applied in altered system, it's been done so in a piecemeal fashion and oriented towards very specific goals. And your uncertainty increases as you consider using a riverine tool in an estuary, and even further in as highly altered an estuary as ours. The main difference between rivers and estuaries are that estuaries are more complex in terms of biology and ecological interactions. And the reasons are due to fresh and saltwater mixing, bidirectional tidal flow, and antecedent conditions. The bottom line is, in estuaries, the body of literature is small relative to rivers, and we have a limited understanding of the effects of flow. I'd like to leave you with I didn't try to do that. Oh, okay. I'd like to leave you with this figure depicting the progression of uncertainty associated with using natural flow regime in an altered system and trying to apply it in a highly altered estuary. Now I want to talk about what this uncertainty means when you consider using natural flow in our estuary. There are some things that flows from reservoirs will not fix. They are not going to restore habitat complexity without physical restoration. They won't supply a depositional material and its associated benefits of turbidity because the sediments are captured behind our dams. It won't restore widespread seasonal floodplain inundation without physical changes because we've channelized our rivers and levied our lands. And Dr. Hansen will be talking about that in more detail after me. Reservoir flows won't restore natural nutrient balance. In a natural system, river inflow enriches the nutrient-poor ocean water, but that function is largely decoupled in our system. In our altered system, municipal and agricultural discharges cause nutrient pollution and a nutrient imbalance that more flow won't fix. And Dr. Glibbert will be discussing that in more detail later this morning. And reservoir releases will not decrease delta water temperature. The reservoirs are too far upstream, and delta water temperature is driven by the ambient air temperature. In addition, depleting our reservoirs will use up the cold water pool for winter run. And Dr. Hansen will be talking about that in more detail in the next workshop. Now I want to focus on one more function of flow, and that is the low salinity zone. A recommendation proposed in several of the submittals is to use flow to maintain the low salinity zone in a specific location to sustain a healthy ecosystem. One such recommendation is to put the low salinity zone specifically between 60 and 74 kilometers, and that represents the Sassoon complex. First of all, I did not find a citation in the submittals supporting specifically 60 to 74 kilometers. And based on my review, it's not supported by the available literature, and the role of the low salinity zone in species declines is uncertain. Oops, sorry. Sorry, I got confused. Proposed. I don't know which way I'm going. Which way is up? Oh, I'm doing it backwards. Sorry about that. I'll get there is no positive correlation between phytoplankton and flow in Sassoon Bay after the invasion of the clam. There's no correlation between X2 and delta smelt abundance or distribution. The delta smelt distribution is shifted to a more northerly and fresher location. I'm missing a slide, by the way. That's why I got confused. So you just have to listen to me at this point. There's no correlation between X2 and delta smelt abundance or distribution. The delta smelt distribution has shifted to a more northerly and fresher location in the Cache Slough complex. And although longfin in the midwater trawl is correlated to flow, it isn't similarly correlated with low salinity habitat. Therefore, some other mechanisms correlated with flow are affecting longfin abundance. The proposed in addition, yeah, this is the right slide now. In addition, last March, the EPA convened a workshop on the low salinity zone in preparation for this workshop. At the conclusion of that workshop, EPA conceded that the role of the low salinity zone in regards to species declines is uncertain. And last fall, the state and federal agencies coordinated in an extensive investigation of the low salinity zone in relation to delta smelt. Their conclusion at this time, as several people said yesterday, is that the role of this low salinity zone was inconclusive. I also noticed that the underlying mechanisms for using flow to maintain the low salinity zone in the Sassoon complex were not accounted for. As far back as 1995, JASB cautioned, by ignoring variables other than X2, we run the risk of imposing inappropriate standards. The fact of a mere correlation is not sufficient to impose something like X2 in a regulatory policy. 2002, Kimmer recognized that no mechanism has been conclusively shown to underlie the relationship between flow and any species. So on a related topic to this specific location of the low salinity zone is an assertion in one of the submittals that the low salinity zone is disconnected from food and turbidity. Again, in my review, this is not supported by the literature, and in some circumstances might be contradicted. For instance, phytoplankton collapsed in Suisun Bay after the clam. In the 2011 FLASH study, phytoplankton was lower in the Suisun complex and higher upstream and downstream of it. And the delta smelt growth rate was not related to salinity ranges. And this is part of the reason for the inconclusive FLASH results. Some researchers have found the potential for food supply in Suisun Marsh and concluded by recommending that we should restore more marsh habitat, and we agree with that. So based on my review of the available scientific literature, given the highly altered state of our delta, trying to use natural flow to restore biological functions would be highly uncertain. Yesterday, DWR and some other people said that flow defines an estuary, but I would like to clarify that by saying freshwater flow defines low salinity water in our estuary. There are multiple factors that define flow in an estuarine ecosystem. The dynamic interaction between fresh and salt water, geometry, diversity of habitats, a functional nutrient balance, good water quality, a functional food web, and a functional species composition. And under our highly altered circumstance and diminished flow functions, I say that there are multiple factors that define our estuary. Therefore, at this time, any large changes of flow made under scientific uncertainty could lead to large adverse impacts to beneficial uses. Thank you.
Thank you, Sheila. Our next speaker will be Dr. Chuck Hansen talking about habitat and invasive species.
Good morning. What I'd like to focus on are changes that have occurred in the Bay Delta physical landscape over time, and importantly, how those physical landscape changes have altered the functions that flow provides with respect to fishery habitat. And this graphic depicts the historic conditions that occurred within the Delta, extensive tidal wetlands, shallow water that promoted biodiversity within a complex array of dendritic channels. We had velocity refuges, we had food production, there were seasonally inundated floodplains that provided habitat for juvenile fish like Chinook salmons to rear, as well as split tail for spawning. And the dams were not in place, so salmonids had access to higher elevation, colder habitats that met their life history requirements by geographically moving further upstream in the system. Here's a depiction of our current system. We've lost a tremendous amount of the tidal wetlands, about 90+%. That was done through reclamation of islands, through construction of levees, most of which are now supported and strengthened by riprap. We've had channelization and dredging for commercial shipping transport. We've had altered hydrodynamics as a function of not only the upstream dams for flood control and water supply, but we've also had increased diversions from the South Delta, within the Delta, many, many diversions, as well as diversions in the upstream parts of the watershed. We've had a loss of floodplain access as a result of the construction of these levees that has reduced substantially the availability of floodplain habitat for rearing and for spawning. We've had as a result of the dam construction, reduced sediment inputs and gravels that are important in terms of providing habitat quality and availability for spawning and for other biological purposes. And we've had the rim dams that have now precluded access for these anadromous salmonids to utilize the upper parts of the watershed, and have now restricted their geographic distribution to lower elevations within the system. And I'm going to show a brief aerial animation to simply illustrate these changes. You can see in this animation that the historic delta was extensively wetlands, many small channels, a large number of dendritic channels